Hello, everyone. Thank you to everyone who has joined just a minute early. We will begin with an introductory presentation in just a moment. So I hope you all can see my screen well and good. Thank you everyone for coming and welcome to our separations webinar titled Advancements in Analysis of Biomarkers via Gas Chromatography. So I want to begin this webinar with a little bit about MDPI. So MDPI is a pioneer in scholarly open access publishing and has supported academic communities since 1996. Based in Basel, Switzerland, MDPI has the mission to foster open scientific exchange in all forms across all disciplines and fields. Our 481 diverse and open access journals, including 472 peer-reviewed journals and 9 conference journals, are supported by more than 295,000 academic experts who share a mission, values, and commitment to providing high-quality service for our authors. Now, a little bit more about the journal that this webinar is affiliated with. Separations is an international peer-reviewed open access journal on separation and purification science and technology in all areas of chemical, biological, physical science, and separation performance, and is published monthly online by MDPI. Now here we have just a brief overview of the schedule you all can expect of this webinar for today. In just a couple moments, I will be passing the floor off to our chair or webinar chair, Dr. Mark Woolam. Briefly following this will be our first speaker, Dr. Waqar Ahmed, who will be presenting on measuring environmental exposure to pollutants and particulates in human samples using gas chromatography. We do also have time for a Q&A session after each speaker, so if you have any questions following the presentation, do make note. Our next speaker of the day will be Dr. David Alonso, who will be speaking on emerging technologies for the untargeted characterization of volatile organic molecules and biological matrices. His presentation will additionally be followed by a Q&A. Heading into the second half of the webinar, we will have our third speaker, Dr. Jonathan Grandy, who will be presenting on integrated VOC analysis from breath to biofluids, building scalable workflows for discovery. As you can see, we have the theme of a Q&A here, so his presentation will also be followed by a Q&A. Please do make note of any questions you have for our speakers. Our last speaker of the day will be Associate Professor Heather Bean, who will be presenting on discovering breath biomarkers of fatigue through chromatography and chemometrics. Then we will have our last Q&A of the day, followed by our closing of the webinar by Mr. Ire Schultz. We do also have a relevant special issue associated with this webinar, which is titled Chromatographic Analysis of Biomarkers. Our very own webinar chair is one of the guest editors, Dr. Mark Woolam, and the deadline for manuscript submissions are December 31st, so be sure to get those submissions in by the end of the year. As you saw earlier, we will have many opportunities as well for Q&As, so please do make use of the Q&A box, which you should see that tool at the very bottom of your screen there. Last but not least, thank you all so much for listening to my introduction. I am now going to pass the mic off to our webinar chair, Dr. Mark Woolam.
Hello, everyone. Thank you so much for joining today. This wouldn't be possible without you all, so first and foremost. And it's really my pleasure to present this webinar focused on chromatographic analysis of biomarkers. I've been working in this space for the last 7 years, and today we pulled a really good list of speakers, both experts in academia and industry, to talk broadly across these topics. I'm very excited to kickstart it off, and I would like to introduce, I'll just keep this very brief. I'd like to introduce Mr. Arai Scholes, who will kickstart the webinar and introduce our first speaker. And make sure you type in all your questions into the Q&A. I think we're going to have some really, really good and fruitful discussions.
Thank you, Mark. Yeah, I'm going to keep it even shorter. So I'm going to introduce our first speaker today, Dr. Waqar Ahmed. He is a research fellow at the University of Manchester in the respiratory group. where his expertise lies in the application of metabolomics to clinical breath research. He was recently awarded the Anton Amann Award by the International Association for Breath Research, and has been highlighted as an emerging investigator in the American Thoracic Society's Blue Journal. His current research focuses on understanding the significance of microbial and environmental exposures in chronic respiratory disease and how they can be monitored and prevented towards improving health outcomes. So I'm going to mute myself now and give the floor to Dr. Ahmet. So yeah, please take it away.
Thank you very much for that introduction. So let me just share. Right, okay, thank you so much for that introduction. So I'm Waqar. I'm based at Manchester University. I'm actually based at the Northwest Lung Centre here in Manchester, which is one of the largest respiratory clinics in Europe. And so there's a reason why it's the largest, and that's because Manchester is an old industrial city and it has a long history of environmental pollution. So naturally, people that lived in the city and close to and worked in the city had high exposure levels to toxic emissions. And in fact, the Northwest Lung Centre itself is based on the grounds of an old TB sanatorium that housed people that were sick away from the city's pollution. So we're naturally very interested to know how pollution, particularly inhaled pollution, may affect respiratory health and subsequent clinical interventions. And so for the past few years, we've been exploring how exhaled breath volatiles contain useful biomarkers of lung disease. But we've also started to appreciate the level of exogenous compounds that might arise from personal exposures within breath. And that's something that we commonly see in our breath samples, especially in our outpatient clinics, where patients have already been exposed to anthropogenic or biogenic exposures outside the clinic. So say, for example, traffic pollution or plant-based diets can be an exposure. And then we see that in the clinic in breath samples. So on the right here at the top, you see a volcano plot. And from our 300 or so patients and 300-400 compounds that we've identified, only these are increased in smokers. So our typical BTEX compounds and furans that we have known for decades that are associated with smoking, we see that in breath quite commonly, and that's not surprising at all. But the interest is how that affects disease, whether there's biomarkers that are also similar aromatic compounds that we're interested in. Another example here on the right, bottom right, is that we see compounds like limonene increased in breath from people who have been having orange juice or some fruit drinks. So limonene is quite a versatile compound. It's quite common in cosmetics, in food stuff, and cleaning products as well. And so you see that increased. And so it's a question of how that affects disease state. So to explore the mechanism of how these pollutants directly affect disease, it was clear to us that these associations needed validation by controlled inhalation studies. So these are quite common in clinic, where they do challenge tests in occupational clinics, where a clinician is trying to find out the source of your exposure, and so they make you do the work in a simulated environment. Say if you're a baker, they'll make you bake some bread and expose you to some antibodies or some proteins within the wheat flour, and then measure your reaction after that. So and a lot of other studies have been looking at diesel fumes. The EPA have done quite a lot of controlled inhalation exposure studies. So it's not uncommon to do this, but it is very difficult logistically, of course. As you can imagine, you need people in a certain environment, you need the ethics in place. And the advantages of a controlled study, of course, is that you can track the toxicokinetics. So what the pollutant, or how the body deals with the pollutants, or how it's absorbed and how it's metabolized and eliminated, if it accumulates in the tissues, and also the toxicodynamics, so how the body deals with the pollutants. So is there an inflammatory reaction? Does it metabolize straight away and get rid of the compound, hydroxylate the compound, say, for example, and is eliminated in urine? What effect does this have on cellular uptake and signaling within the body? So it's very interesting to know the mechanistic toxicology, something that you are going to have difficulty finding in a large epidemiological study. The other advantage, of course, is that you're isolating certain exposures, say, for example, indoor air exposures or traffic-related exposures, and you can really characterize and dose a precise amount of a compound to a person within a controlled environment. So this picture on the bottom right here is of a simulated kitchen in this ingenious project in the UK, and there's a PTR instrument somewhere, I think, in a different room, but it collects cooking exposures, and so somebody will cook something in that environment for a couple of hours, and then they'd measure what VOCs are in that environment. And of course, you're interested in things like secondary organic aerosol formation from VOCs, which is difficult to build that mechanism outside of a controlled environment. And so these controlled studies can also be complementary to epidemiological association studies. Of course, there's pros and cons in that the epidemiological studies can have thousands of patients and you get really good numbers, whereas the control studies is difficult. It's a very specific environment. Maybe it's not so generalizable to the outside real world, but if you have a simulated environment, that might be. So at Manchester, we have such a simulated chamber facility here. So you can see the chamber. You see my mouse that behind this enclosure. The chamber is just an 80-meter squared Teflon bag, which has different sensors for controlling temperature and relative humidity. And you see some halogen lamps in there as well for photo oxidation experiments and things like that. So there's more details in this reference here if you want to read about the facility itself. And so that's been there for a long time. A lot of environmental research has taken place there, of course, for diesel engine exhaust fumes and more atmospheric conditions, atmospheric air pollution in Manchester especially. And more recently, the MAC was used for human inhalation exposure. So a small pilot study was performed, the reference is there, and that pilot study exposed people at risk of dementia to common pollutants that we're exposed to on a daily basis. And the aim of the study was to try and find out if there was a change in cognitive function. And so about 13 participants were recruited, and this was a crossover study design. So it meant that each participant had a control exposure, clean air exposure, and then each of the exposures that I'm going to list in the next slide, they had each of those exposures before and after. So they all got a bit of each exposure. And that was carried out for about 60 minutes. Of course, with the ethics, you needed a medical doctor there to monitor, especially 24 hours, 72 hours after the exposure as well, by phone call. And so in this study, before and after exposure, cognitive tests were carried out, and blood was collected 2 hours before and 24 hours before exposure. And that's what I was more interested in, trying to see if we can extract any metabolism effect or at least pollutants in blood. So these were the 4 exposures. The first two are mainly indoor air pollution exposures, so cooking fumes. I think they tried to standardize the cooking fume exposure, so they used 2 pork chops, and it was just to simulate frying, because that creates some terpenes and some PAHs, as was published before, and so the emissions from this cooking fume enclosure were then fed into the larger MAC, and then people were able to breathe this in later for about an hour. For cleaning products are quite harmful. So what was done is limonene was only used to create the secondary aerosols, secondary organic aerosols reacting with ozone. So that was measured. It was all within safe limits, and of course, and then the other two, the next two, were diesel exhaust and wood smoke. And these are the more outside environmental, outdoor pollution exposures that you would expect. So they have a diesel engine in there that was idling for 5 minutes, and part of that emissions was teed into the MAC, as you can see behind that room there. And so until the safe particulate matter level was reached. And for wood smoke, they had a wood burner outside the lab. And again, just like with diesel exhaust, not 100%, but a small portion of that smoke that came out from the wood fire was fed into the MAC, and that was allowed to accumulate, equilibrate, and until a certain amount of compounds were reasonably measured, then they were exposed to the participants on the other side of the MAC. So my interest was looking at the blood samples. So I was able to get hold of the blood plasma that was sampled before and after the exposure. So it's important to note here that it was 24 hours after exposure. And so what we did was pool all the samples together into exposure type and pre and post exposure, and participate the proteins with a 3-to-1 ratio of ice cold methanol. That allowed us to separate out all the compounds away from most of the bulk material. And some of that supernatant were then dried and in a centrifugal evaporator for analysis. So for our analysis, we used an automated online derivatization method on our GCMS, and that was a typical MOX TMS derivatization. So that would, of course, add the oxyamine groups to ketones and aldehydes, and then the second reaction, acylation, would add the silane group to the TMS groups to these alcohols and amine compounds, so that they'll be able to derivatize and analyze in the GCMS later on. So we used the GCMS GC Orbitrap Q-Exactive that we have in the lab to automate that. Just a normal, regular, non-polar column. And this was more of an untargeted analysis, nothing specific to any certain SVOCs. So this is a general untargeted extraction and derivatization. So we can see all compounds, or most of the compounds and metabolites in the blood plasma. And so process the data, we used MS-DIAL to pre-process and align peaks, and MetaboAnalyst to perform untargeted statistical analysis. And so all the data that I'm going to show you is just a volcano plots. This is still ongoing analysis, but they've all been FDR corrected. So anything that's increased would be on the top right box here. So we also sampled clean air. Each patient was able to get a clean air control and a before and after control. So in clean air, we don't see anything increased, but a couple of compounds here. So each of these dots here is a feature. So we assume that it's a compound. And so 2 of them have decreased 24 hours later, which is interesting. And our first result actually shows that for the indoor air exposures, or what we like to call indoor air for cleaning products and cooking fumes, that was the same kind of result, that we didn't get anything increased significantly, but there were a few compounds or we didn't get anything significantly increased 24 hours after exposure, but we do get some increase in the control in the 2 hours prior to exposure. And so what that might be is that it could be an alternative toxicokinetic profile. So if you're breathing in very light, low molecular weight volatile compounds, it's likely that they could be breathed out straight away, so you're not going to get them in the blood. It's also possible that they could be metabolized straight away and then excreted through urine or sebum. So that's entirely possible. So it's difficult to know, especially if you don't have those bloods between the exposure and 24 hours. But that's a different result for the more combustion-derived or the outdoor air pollution exposures with wood smoke and diesel exhaust, which did have quite a few significantly increased compounds after exposure. And especially for diesel exhaust, there are quite a few features there that have been highlighted. And just by a quick look on NIST, a few of these are most of these are metabolites, things like sugars and lipids that have increased here. There are some compounds that are more pollutant, not very endogenous, but I'd have to confirm those. But for wood smoke, there's far less compounds. There's a few here that are increased after exposure, and one there that's increased prior to exposure. So that could be just the variation that you have between the 2 hour prior and 24 hours after exposure. And these are more likely to be an effect of the exposure metabolism, metabolic effect of the exposure. And so a mixture of that and accumulation of some of these pollutants. And so, yeah, just to summarize, so what we found is that inhaled pollutants are highly dynamic. I don't think that's a surprise to anyone really, but it's interesting to see that there's changes in the blood from a controlled exposure, and so that's something that we're going to continue and to explore in the next few years. And we've sort of shown that the controlled exposure are important to validate biomarkers. So there are a few exposure biomarkers that the health and safety executive in the UK do measure, but it's always on request by a company that might have exposures within the work environment. And I think that it needs to be more integrated into clinical analysis. So just like we measure steroids and cholesterols, it might be important, especially for respiratory diseases, to look at certain biomarkers from pollution exposure that could have an impact on disease. And so there's a mix of old epidemiological data. So by that I mean birth cohorts and large multinational studies that sample blood. Like NHANES is one good example, where over a certain number of years you collect a large population or collect samples from a large population. But it's difficult, like with cooking exposures and clean products, to assess certain compounds, especially if they're breathed out or urinated straight away and eliminated out straight away. So it's difficult to assess those and the toxicity that they might have, even if it's a short period of time, on that person and on respiratory diseases. So the future work would be to look at more mixed exposure studies, make it a bit more complex, so we're we're not just exposed to cooking fumes or diesel exhaust or tire wear. It might be a combination of all these things. And that's something that we can do at the MAC. And I'd like to look at things like breath and urine. That's something that we're setting up for in the MAC as well. We've got a PTR there, so we can look at breath almost immediately in real time, breath VOCs, that is. And so the next, of course, the next phase is to look at the mechanism in respiratory diseases. Of course, that might be difficult to recruit patients, but looking at people with mild diseases like mild asthma might be possible. So yeah, thank you for listening. I just want to highlight that I also have a special issue, but it's not in the same journal, it's in Metabolites. So if you want to submit something that's more specific to breath biomarker discovery, then you can take a photo of that. Yeah, thank you.
Thank you very much, Dr. Ahmed. We're actually running ahead of schedule here. If anyone would like to throw a question into the Q&A section, don't be shy. I'll give it maybe a minute or two. But if no one has anything beyond after that, we can move on to Dr. Alonso's talk. So
I have a quick question, Dr. Ahmed. So you definitely touched upon the potential correlations from the blood metabolites to the exposed breath-based compounds. And that was kind of what was going through my mind the entire time. And if you could just speak to that a little more, on what you would anticipate and what targets you're, because like the example that always comes to mind is the exposure to limonene and the oxidation to its, secondary terpenoid. And I think understanding transitions in the volatile organic compound profile between these biofluids might be the key to really understanding how they're transforming in our bodies.
Yeah, absolutely. Yeah, it's a great insight. I think that we've shown that through a peppermint cohort consortium study. Not we, but other research groups have, where eating a peppermint capsule or drinking orange juice takes about 2 hours until you breathe it out as a compound. So in the opposite way, it's difficult to then assess whether you're breathing in limonene and whether it's being breathed out again, whether it's too volatile or it's going through the blood. We certainly see it in sebum, so we see it in the oily part of the skin. So that's very interesting. That's just a few experiments that we did. And so, yeah, it's very something that we probably need to all work on, especially in the breath community, looking at these volatiles and where they come from exactly in the blood. And so that's what led us to look at that sort of thing. We know that limonene is very common compound everywhere in perfumes, in food stuff. So it's very interesting, I think. Hopefully we'll be able to expose patients to limonene, but it's difficult because you don't want to make them react under these controlled conditions, but there's certain situations that they can do in these challenge studies that they have. So that's something that a colleague of mine is working on. Actually, one of the PIs of this HipTalk study is looking at exposing people to limonene and seeing how, or asthmatics to limonene and seeing how they react. So that would be quite cool.
Hi, Waqar. I'm just going to follow up on that discussion that you and Mark were having. So with challenge studies, are there opportunities to use isotopically enriched compounds to help with the tracing, or are there any additional complications just with the human subjects and the ethics and protections for doing something like that?
Yeah, it's all unknown, uncharted waters. So with our challenge studies at the moment, as far as I know, I'm not a clinician. So the clinician that in question, Huda, she's an occupational asthma clinician, and so they have guidelines on what defines occupational or work-related asthma already. And in that definition, I'm not sure limonene exposure fits quite well. It might be a new, like I think with isocyanates, there's a specific diagnostic. So I'm not sure. I don't know if it's been done before, but that would be quite interesting, especially isotopic. I mean, the only isotopic labeled compound that I know is 13C urea, but that's ingested. I have asked the questions about inhaling isotopic labeled, and the answer that I got from an environmental chemist is that the carbon isotopes would be much safer than deuterated ones. But beyond that, it's only if you apply for an ethics application that you know. It's more difficult doing it in the UK. I know in Lund University, I think that's in Sweden. I don't know. Yeah, so they have deuterated phthalates that they've exposed to people, so that's very interesting. And they can see that, they can track it through blood, but it might be more possible in America than the US than the UK right now.
Yeah. Okay, thank you.
Yeah, I think there's another carbon-13 methacetin test. So I think there's 2 isotopically labeled breath tests, and yeah, I love the idea of trying to do it with like limonene.
Excellent.
Yeah.
But yeah, thank you for the questions. I don't see any in the Q&A box or the chat box. So I am going to go ahead and introduce our second speaker, Dr. David Alonso. He is an applications chemist at the LACO Corporation based out in St. Joseph, Michigan. He specializes in the use of modern instrumental tools such as NMR, IR, and mass spec for the analysis of complex samples. And his current work focuses on the utilization of multi-dimensional chromatography and high-resolution time-of-flight mass spectrometry for the analysis of metabolomics in environmental samples. Additionally, he is interested in the analytes of forensic drugs such as synthetic opioids, such as fentanyl analogs and cannabinoids. Dr. Alonso, the floor is yours.
Thank you very much for the introduction. And also thank you to the organizers for the opportunity to share some of the work that we conduct at LACO Corporation. And the title today is Emerging Technologies for the Untargeted Characterization of Volatile Organic Molecules and Biological Matrices. And the matrix we're going to focus on today is urine. And this is a preliminary project that we conducted with Dr. Woolham and other researchers at the Indiana University at Indianapolis. Here's an outline of the presentation, which will include an objective, some of the analytical challenges that we experienced during this preliminary project. We'll look at the instrumentation used to collect the data, the workflow, and then we'll jump into the analysis results. We'll look at some of the representative compounds that we found in urine during this comprehensive analysis, and talk about how we confidently annotate compounds or sample constituents. And finally, we'll look at some statistical data processing and end with a short summary. So prostate cancer is the most prevalent for men and second leading cause of cancer-related deaths among males in the USA. Current screening methods include digital rectal examinations, PSA tests, and these tests are good and commonly used every day, but they may give bad results. So there is a need to develop complementary non-invasive screening tests for prostate cancer. And one option is monitoring volatile organic compounds or VOCs in urine. So the objective of this study was to develop analytical methodology for the annotation of VOC candidate prostate cancer biomarkers in urine. There is a major challenge pointed out by researchers, and that is that the composition of urine, unfortunately, is highly dynamic and exhibits high variability, both within and across individuals due to numerous factors such as age, diet, and activity. There are additional analytical challenges, including the large number of sample constituents, the differing physical and chemical properties, and the large concentration ranges of these constituents. The emerging technology that we're going to use for this comprehensive analysis is a combination of enhanced chromatography, high-resolution mass spectrometry, and of course, to handle this high-quality, very rich data, we need some powerful software. And the instrument that we used to collect the data was the LICO Pegasus high-resolution time-of-flight mass spectrometer. Mass accuracy of 1 part per million, resolution 50,000. And one of the important parts, of course, is the acquisition speed to properly define peaks in this experiment, and that is 200 spectra per second. And ionization, we'll look at 3 different modes: electron ionization, positive and negative chemical ionization. To the right, we have a nice little scheme of the instrument where we show the GC. It has actually 2 columns, a longer first dimension column and a shorter second dimension column of different phase. And in between, we have a modulator. I like to call it the pacemaker. It's connected, of course, to this unique mass analyzer with a folded flight path via this transfer line. So if you're not familiar with GC by GC, we step back a little bit and look at GC MS. And we have an inlet, we can inject the material onto the column, and hopefully you'll get decent separation and a nice little chromatogram. But those of you who perform this experiment know that separation is not perfect, and often there are a lot of compounds that co-elute in this GC MS experiment. So what we've done is we've added a modulator which serves to cryogenically focus anything that comes out of the primary column and rapidly inject it into that second column of different phase. And what you get instead of a chromatogram now is separation and generation of a map, a contour plot, or an XY plot of your sample. And I'll use those terms interchangeably during this talk. So you'll have first dimension separation, that's down in the x-axis, and second dimension separation. And hopefully anything that's co-eluted in this, let's say this peak right here, can be separated by adding this extra column of different phase. The workflow, well, we first of all started in this preliminary study with 20 normal samples and 20 disease samples. We prepared or introduced the material into our system or our instrument using headspace, solid phase micro extraction, and we use Chromatoph software for instrument control, data acquisition, and data processing. And that processing involves untargeted processing with software deconvolution, database comparisons to very large, well-established libraries such as the NIST library, the Wiley library. We also have the ability to perform a lot of filtering. In this case, I perform retention index filtering. And since we're dealing with high resolution accurate mass ions, we can perform formula determinations for fragments, molecular ions, and if we're doing chemical ionization, we can get formulas for those adducts. So here I show the results, a map for a urine sample. And here's the x-axis, the primary axis, of course, the secondary axis. And you can see that you have a bunch of peaks. And of course, EI is universal ionization with one source that can also, in a separate run, maybe add a line to the queue. I can analyze and get the positive chemical ionization information, which is a softer ionization, and it'll complement the EI data that we collected. And this is, of course, selective for electron-rich compounds, and we can perform another acquisition in negative chemical ionization mode and get selective ionization for electron-deficient species. We have also the added benefit that there'll be a very good increase in sensitivity for those electron-poor compounds. If we focus in on the contour plot or map or XY plot of the EI data, we can see that first dimension of separation, which by the way is much longer than the y-axis, or the second dimension of separation. And remember that we have different separation mechanisms. And so you will identify more compounds because of the improved or enhanced chromatographic resolution. You'll have better signal to noise, cleaner spectra, improved database comparisons, and there's more annotations. And we conservatively say that it's 2 times, but it's often 4 times to 5 times more annotation as compared to the regular GCMS experiment. And there's group clustering on this map. There are neighborhoods, in other words, where the monoterpenes occur, the sesquiterpenes. If you have some diterpenes, we know where the neighborhoods for those species are. In addition to that, there's aromatic aldehydes, linear aldehydes, and ketones, and so forth, as well as a bunch of alkanes. The experiment also allows us to separate some of the material that we're not interested in, such as septableed or dimethylated cyclosiloxanes, as well as column bleed. Once we process the data, of course, we can get a lot of information. Now, we have the ability with this technique to acquire both GC or 1D data, as well as GC by GC. It's just a simple check of the box of which technique you would like to use. So what I've done here is I've selected to perform the 1D experiment. I get my typical chromatogram. And out of the compounds, I've selected 4 pairs of compounds that happen to colute in this chromatogram. And after automated processing, you'll get names of these compounds, you'll get the retention times, and you'll get similarity scores. And that's the database matching. How good does your observed data, how good is it when you compare it to the, let's say, the NIST library? A perfect score would be 1,000. 800 and above is respectable. And you can see for these pairs of compounds, we have some decent values, some poor values, and unfortunately, these last 2, or this last pair, G and H, were not found during automated processing. So I decided to check the box, run the same sample, inject and carry out the GC by GC experiment. Now I have the retention times. Remember that this is an XY plot. And so there's 2 values, and you can see if you compare the similarities, not only is there improvement in the similarity, but compounds that were not detected during automated processing in the 1D experiment are now detected in the 2D or GC by GC experiment. And you can see that second dimension of separation on the contour plot shown below the GCHRT TIC. So I mentioned that the list of compounds, and in urine, I was surprised using our extraction technique, Headspace SPEME, how many compounds indeed we found. And the peak table reveals that we have a wide variety of different compounds. Again, the names of the compounds, the formulas. This is the GC by GC data, so it'll be 2 values, spectral similarity scores out of a perfect score of 1,000. And if the molecular ion is present, sometimes it's present in EI spectra, sometimes it's not. It depends on the compound. I display it, the mass accuracy in this last column in terms of parts per million. But there's a wide variety of compounds. Don't worry, we don't have to look at all these compounds, but the average spectral similarity was 847 out of a perfect score of 1,000. But we should look at the underlying data. How do we annotate these compounds? Well, we look at, first of all, spectral similarity. The observed high-resolution accurate mass data is on the top. The first hit in this database comparison is shown down below, and the assigned spectral similarity value is 784 out of 1,000. But we just don't rely on spectral similarity. We also can look at the mass accuracy. And if we focus in and zoom in on this really tiny portion of the spectra, we can bring it up and show that we found a molecular ion for that species with a mass accuracy of minus 0.52 part per million. That value, together with this marginal spectral similarity score, gives us an increased confidence for compound annotation. And of course, the mass accuracy is just the observed minus the calculated divided by the calculated times a million. Not only can we look at the molecular ion, we can also get mass accuracy values and also formulas for any of the ions in this high resolution accurate mass spectrum. And again, just increasing the confidence for compound annotation. I did collect a second or I added a second line to my acquisition queue and collected both NCI, or negative chemical ionization data. In addition to that, you will see that I also collected positive chemical ionization data. So this data is going to be complementary. So where I had a very small molecular ion in the electron ionization data, a marginal spectral similarity score, now I have an intense molecular anion with a mass accuracy of minus 1.27 parts per million. And then the software also generates a theoretical monoisotopic cluster, and it compares the observed and the theoretically generated and assigns it an isotopic fidelity. Anything above 900 out of a perfect score of 1000 is good. So we can look at a couple of compounds here. We're going to go through a couple of examples. One is where we have a pretty decent spectral similarity. Again, the peak true observed data is at the top. The library match is at the bottom. Unfortunately, there's no molecular ion. That's not a problem because when we collected the positive chemical ionization data, now we have a strong protonated molecular ion with a mass accuracy of minus 1.54 parts per million. We're using methane in this case as a reagent gas, so there's additional adducts, the M plus 29 and also the M plus 41, and they also exhibit exceptional mass accuracy. And of course, we have a nice isotopic fidelity, so we're pretty confident with that annotation. Now, sometimes you have a particular hit that's pretty good. It's above 800 for this aldehyde, linear aldehyde. And the score is 863 out of 1,000. Unfortunately, there's no molecular ion in the mass spectrum for that compound. So you have to go over to the positive chemical ionization data, and now you get a strong protonated molecular ion with associated adducts with a mass accuracy of minus 0.4 parts per million, and we can see that the initial assignment via spectral similarity score was incorrect. The actual compound is another aldehyde. So once we're confident we have our list of compounds, now we need to compare the data between the normal and the diseased samples. And we use Chromatoph Tile. It's a piece of software that can handle this rich, high-quality data. And we use Chromatoph Tile for this comparison to try to look for compounds that differentiate the two groups, diseased and controlled. And this software is based on work conducted by Professor Sinovac at the University of Washington. And we're going to use Fisher ratios, or the class-to-class variation divided by the within-class variation. And higher values, of course, make the compounds more significant. This is what the user interface looks like. We have a nice little representation of the data for the first hit in the library. We have a nice bar chart with, I don't have all the samples listed here, but the blue ones are the normal ones, the red ones are the disease ones. We have a corresponding principal component plot, or PCA plot, as well as some of the compounds that differentiate the samples. It also has a nice heat map associated with this interface. And I took a small list of representative potential or candidate VOC biomarkers for prostate cancer. And there's some unique compounds here, such as alcohols and aldehydes and ketones and so forth. For example, this particular 2-tetradecanone also has been tagged as a potential biomarker in a recent paper that was published in 2025, or compounds such as fatty acids, which are also been implicated or tagged as potential biomarkers for prostate cancer. So in summary, GC by GC high resolution time of flight is a powerful tool for the untargeted characterization of volatile organic compounds in urine. And we characterize and annotate these compounds using database comparisons, but for increased confidence, we also use formula determinations. We also can increase the number of compounds that we can annotate by performing the GC by GC experiment. If we have compounds that collude in the first dimension, we can separate them by performing the GC, or in other words, adding this extra dimension of separation. We also use complementary EI and CI data that can be positive or negative. It aligns very nicely because we're using one source for even more confidence in compound characterization. And finally, the data that's generated is very, very rich. And we have software that can handle and process the data in a reasonable amount of time. And with that, I'd like to thank you very much for your attention. And if there's time, I can answer some questions.
Thank you so much, Dr. Alonso. Yeah, if there are any questions, I will happily read them out. Dr. Bean, yeah, go ahead.
Hi, David. I got curious as you were presenting about performing the silylation reactions, and I've never thought about this before. I don't run chemical ionization, not in the past 2 decades anyway. How much does the silylation reaction affect what you can ionize by chemical ionization? Does it just remove those compounds as being candidates for chemical ionization, or is there some opportunity still to see those compounds when you've already added more or less an adduct to those sites?
Yeah, no, I think that for example, silylation, or we can perform the two-step derivatization. There's no problem at all in looking at both the complementary EI and positive chemical ionization. You'll struggle for the silylated species to find many interesting compounds in the negative chemical ionization data, but you do run it in case you're interested in some exposure or anything like that, maybe some pollutants that are in there that will be highlighted in the negative chemical ionization. But it's an experiment that I've conducted often, especially with plasma. The beauty about this experiment, and it was this is new to me, and Dr. Woolham introduced me to this technique because I've done urine before using normal sample prep and liquid injections. This is the first time I use headspace beaming, and I was surprised at how many compounds we were able to observe without derivatization, which is amazing. I'd like to, in the future, extend this or the coverage by using, for example, maybe some SPME arrow, maybe some immersion SPME as well. But again, the silylation really hasn't been a problem for me in the past.
Great, thank you. That's helpful to know.
Yeah.
Yeah, Dr. Alonso, amazing talk. Thank you so much. And yeah, I think looking at the the contour plot of the electron ionization, no, it is so clear the benefits of the 2D-GC. But looking at the chemical ionization, I guess my question is two-dimensional chromatography really needed? It doesn't seem like it's as rich as the EI, and it seems like they're pretty well separated in the first dimension.
Yeah, it's kind of deceptive. And I did this for presentation purposes. There is more selectivity with the chemical ionization, uh, but I am zoomed out. Remember, this is a map, and some of the images that you saw, it's like if I was on a drone flying over the data. And I'm at very elevated temperatures, but you'd be surprised if I showed you the peak markers, how many peak markers there are, how many, and those of course correspond to compounds. Is it the same as what you get with EI? Absolutely not. But I like to have that CI information because of, there are cases in EI, it's wonderful. It's a universal ionization, but often you don't get molecular ion information. And that's very important to me if I'm going to be confident in the annotation, for example, of potential biomarkers.
And along with that, like, and we talked about this before, but it just really was apparent with like the tetradecanal and the hexadecanal or the ones. I forget if they were aldehydes or ketones,
There were
but
ketones, yeah.
ketone ones. Why couldn't you just like do nonpolar retention index filtering? And in a lot of cases, also like, why don't you just shoot the pure standard on the column? It seems like it would almost take, I don't know, would it take less or more work compared to running all the samples in positive that's the question I asked though.
No, that's an excellent question. First of all, it depends on how you set up the experiment, and that's a good catch by you. I can set that retention index filtering by casting out a net or the tolerance in terms of retention index filtering. It could be 30 retention index units or 50 retention index units. And the narrower that window is, the better chance that you are going to be able to filter out bad results or bad hits. For example, I could determine if I carried out an experiment, I could easily distinguish between galactose and mannose, even though they have similar spectra. But as far as narrowing that window down to 10 or below, right? That's going to be effective filtering. I typically don't do that unless I use my own user library. So could I've actually distinguished between the two methyl ketones? Absolutely, if I would have narrowed my window. And of course, the ultimate, and that's why I use annotation, I don't say identification. When I run the standard itself, and it's the same retention time, same spectra, that's an ID or an identification. That wouldn't be a problem with that ketone, but there are a lot of compounds, especially, and something I didn't mention is that when I perform this statistical analysis, there are a lot of unknowns. All right. So it just depends if you can get the standard. And finally, the data is very complex. And I apologize for not showing you all the data. In fact, I have some hidden slides that might be scary because I keep adding to that representative list of compounds. But you're absolutely right. I would like to use all of the techniques, retention index filtering, but I also need the complementary techniques just to be sure. I can go to court and say, yes, I think it's this compound, even though I don't have the standard.
That is my favorite of you. You take the compound identification to court and you present a great case, Dr. Alonso. Thank you so much.
Oh, you're welcome. My pleasure.
I have a question, but if it is a long answer, we can skip it for the sake of time. But you mentioned having a folded flight path. Do you have to calibrate it more often because of how long it is and the possible issues that may arise with an extended flight path? And I guess how does that apply when you are running a large sequence of samples? Are you worried about having to potentially calibrate it as you're running large batches, or are you quite confident that it'll sustain, a good amount of calibration throughout running?
I think it'll be pretty. I typically don't tune, and calibration's part of the tune process. I don't like to tune, especially when I don't like to interrupt a batch uh, experiment. Where I'm running a series of samples, metabolomics. I don't want to affect the statistics in any way, shape, or form. The mass calibration's pretty good, and in addition to that, there's drift correction that occurs automatically, and that's a process. I can talk to you later offline after the event. But as far as tuning and calibrating, I do that at the beginning or start of the queue.
Thank you. Yeah, I'd be very intrigued to learn more about the drift correction.
It's a good question. Yep,
Thank you very much.
you're welcome.
Okay. So, for the sake of time, we are going to move on to our third speaker. Dr. Jonathan Grundy. He received his PhD in analytical chemistry from the University of Waterloo, focusing on SPME, TF-SPME, sample prep approaches for GCMS for both environmental and biological samples. He currently works at Sepsolve Analytical in Canada, and he has served a joint role as a service engineer as well as an application scientist, focusing not only on ensuring newly installed thermal desorption, tandem GC, time of flight instrumentation is functioning correctly, but also assisting other scientists in successfully implementing new methods on their systems. I can personally thank Jonathan for that part of his bio because I am one of those people. And this has allowed him to continue analytical method development for human breath and skin volatilome research with others across North America. So, Dr. Grundy, the floor is yours.
Thanks to you, Ray. As he was mentioning, my name is Jonathan Grundy, and I'm currently working at Sepsolve Analytical. So, of course, another instrument manufacturing company. But what I want to speak to you about today, kind of looking at a top-down level from sample introduction to separation and analysis, all the way to data processing, kind of looking at what that workflow looks like in its entirety. So just as a quick introduction to where I'm coming from, what I'm doing. Again, I'm from the Sepsolve side of Schoenenberg Analytics. So I mostly focus on GC by GC approaches, both flow modulated and thermal modulated systems. We have our own benchtop unit and software, but of course, we're partnered up with Marks International. Okay, so sorry about that. So I'm coming from the Sepsolve Analytical side of things. And again, we mostly focus on separation technologies as well as our TOF-MS and data processing suite. But with our partnership with Marks, it allows us to have a fully integrated approach with the sample preparation side as well, mostly focusing on TD. And I'll try not to make this commercially and more so focus on what's really important here for the conference today, and that's talking about how to best set up our approaches for VOC analysis. So many of you here already know why VOCs are important. Of course, a lot of classical bioanalysis assays, whether it's blood or urine. Classically, that's done a lot by liquid extracts, followed by HPLC-MS for identification of biomarkers. But as we know, the breath metabolome, probably the closest thing to what we'd expect touching the tissue of interest is human breath. And of course, a lot of these non-polar VOCs are not easily HPLC amenable, making GCMS approaches really important for this here. It's also really important to highlight that breath analysis gives a much less invasive manner than, say, classical biopsy or even blood extraction. Of course, urine by HPLC is also particularly non-invasive, and this gives it a good potential for at least easy for the patient breath and disease biomarker discovery. So here at Sepsolve in Waterloo, we actually will take a lot of samples from potential collaborators, and the biggest question we'll commonly get asked is, the biggest concern those collaborators may have is, how can I be confident in the results I'm getting? How do I know what was collected is truly representative of that sample? So a lot of words that come up, but confidence is what really comes up. And with that, there's a few questions that kind of guide that. Are my samples secure? Do I have to worry about, we collected this out in a hospital 2,000 kilometers away. Has it picked up background from transport? Are we losing volatiles to the atmosphere during transport or sampling? Is the method repeatable? Are we sure the instrument's response is the same from run to run? How stable are these? In the data that's presented, am I missing any features? I see all these features you've shown, but are we losing anything? So these are kind of the questions we use to guide our workflows. And what I hope to show you today is, particularly in breathomics as we move forward, in that I think TD is coming out to be one of the gold standard approaches for performing this in a reliable manner. And this is still in conjunction with things like TEDLAR and flex coil sampling bags, dedicated sampling masks with captometers and active pumping meters to make sure, pumps to actively make sure we are pulling alveolar breath with the captometer attached to that. This is all drawn onto a TD tube, and at least for our system here, we then always have our collaborators, patients, fully cap these in sealed brass caps with ferrules to make sure that sample is stable for a period of at least 2 weeks. Typically, actually, we found much longer than that. And then finally, when these tubes are loaded on our autosampler, we always make sure these are sealed on both ends with something we call the diff lock cap. And all that really is a spring-loaded cap that, while the sample is sitting there waiting to be run, a spring-loaded mechanism keeps those tubes sealed on both sides. When we load it for desorption, there is actually a probe, a hot and cold nozzle that then pushes on those springs, and then that tube is only opened when we're ready to analyze it, giving us confidence that during transport we haven't picked up a bunch of contaminants. And while it's sitting on our autosampler tray, we're not losing very volatile components that could be of potential interest. Beyond that, we also have a suite of little accessories that we really do recommend, whether it's from us or somebody else in your studies. You want to make sure you have a good means of conditioning and cleaning your tubes. You don't want the features you're seeing just to be background from previous runs. A means to essentially inject liquid analytical standards onto that tube. So it could be a good way to introduce isotopic label standards through a liquid syringe. And that rig allows it to be added in a repeatable manner. And then probably my favorite for breathomics studies, particularly when you have several cohorts that might be, weeks, even months apart, is automated addition of internal standards through a gas cylinder. That way we can adjust and correct for instrument drift during run. Now, the last guy here, this is something I haven't had a chance to use, but this is particularly useful if you need to set up full QC samples. So you can take one tube, spike this with either analytical standard or potentially several tubes from real samples, and then absorb this to 10 to make pooled QCs for statistical analysis and checking data quality. So that's more on the front end on the TD side and how we do sample introduction. On the SEPSOLVE side of things, we also want to be able to perform GC/GC for separation and then detection on a time-of-flight mass spectrometer, as Dr. Alonso had said, very important for the acquisition frequency required for GC/GC analysis. So getting into some actual data from one of our breath studies. Many of you are already familiar with classical one-dimensional GC approaches, and I think Dr. Alonso made a very good justification for GC/GC as well in showing with accurate mass, we have the ability to perform deconvolution, and most deconvolution software is going to be able to separate out these three peaks quite well. The difficulty becomes is within a mound of three peaks like this here, if you have one compound that might be 1 or 2 orders of magnitude less than those larger peaks, there's a good chance it could be missed as noise if we do this on a classical 1D approach. So how can we be sure we're not missing anything in the sample. And this is where we do typically really recommend GC/GC for these type of studies, because once we pull this out onto a second dimension column, anytime we would have had a coelution in the first dimension, so first dimension retention time across the bottom here, second dimension retention time here, anytime we see peaks that would have lined up vertically along that second dimension, so this peak here, this very large one here, and then this tiny peak down here, these would have been coelutions on a standard 1D method. And I'm pretty confident deconvolution, looking at your mass spec, we would have pulled these two peaks apart. But there's a good chance something sitting down here, trace levels very well could be missed. And in a lot of these omics style studies, of course, a lot of times maybe a major peak that distinguishes samples, but we don't want to miss out potential biomarkers. So they're sitting down at the parts per trillion level just because we have some common compounds that are sitting up at parts per million and absolutely masking everything sitting underneath it. So this is kind of our justification for why GC/GC is important. And referring to Dr. Alonso's talk, this is looking down back at that chromatogram. Now you can kind of see what some of those tiny peaks may look like that you may miss depending on how you're showing your contour plot. So moving forward to that contour plot, this is what that three-dimensional plot will actually look like for a breath sample. And we can see for many of you in the breath omics field, these are, of course, some peaks you may recognize, but you can then see group type separation going from bottom to top. We have a reverse phase column. So our least polar species that were less retained in the first dimension column are then better retained in the non-polar second dimension column. So you're seeing your alkanes sitting up top and your more polar species sitting on the bottom. And this can also assist when we're trying to identify these peaks. We know that if we start seeing, we get identifications for what is identified as a very polar compound up here. For those in the GC/GC, we know we have no wraparound, and we're seeing an ID for a polar species up here. Well, there's a good chance that's not going to be a correct identification. So that ordered separation across the second dimension can really assist in identifying these unknown species. So we've talked about that separation, the analysis, and the advantages of doing this on GC/GC. But when I work with new customers, new collaborators in this area, the question that always comes up, it's almost like the hidden curse of running GC/GC. People have been used to seeing, tens, maybe up to 100 compounds on their 1D method, and suddenly they're sitting there with a new chromatogram with 700 features that it's like, how do I even look at this data? This is, it is just too much to look at going peak by peak like I used to in a 1D method. And this is where we also would recommend good data processing software. So on our end, we use something known as Chrome Compare Plus. But this is still using the same principle from Professor Senovic's group, the tile-based Fisher analysis approach, where essentially that 2D plot is plotted out in a two-dimensional grid where we have distinctive tiles, and then we look to see if there are peaks identified in one of those little grids there, and we'll compare the signal of that grid across several samples here. Then what we hope for biomarker discovery is then potentially in one of our affected groups, we see an upregulation or an increase in signal across the replicates of our affected group as demonstrated here. So to show this with a real set of samples that we had run, I believe this is from our UK lab who had performed this one here, and this is just a very quick study. We have two compounds from two separate sample groups, 4 replicates each, very small study, just as a proof of concept. We do have other data that has come from collaborative universities and hospitals. Unfortunately, that is their data, and I'm not able to present that as much. So this is something we have internally. But if we quickly look at these two plots here from Group A and Group B, you may notice it's going to be difficult to immediately pick out what compounds are different between those two chromatograms. I can see one here, for example, by eye. But taking that workflow through as one example, we then essentially put this into Chrome Compare Plus, generating a principal component analysis between the two groups. We can see good clustering between the groups here. This will then generate, we then use this to generate a volcano plot where we have significant features shown on the top here with compounds that are downregulated in the affected group shown here, upregulated in the effective group, or essentially you can also consider this upregulated in the control group in blue here. While compounds here have significant signal but are similar, and we consider compounds down here to be insignificant. So just taking one of these compounds from the volcano plot, we can click on this and then go back to our original chromatogram to see what this peak looks like between the two groups. And we can, of course, see that there is an increase in group B of this compound. Then we use our mass spectrometer to identify this as dimethyl sulfide. And similar to other companies' approaches, we will then use this to perform a NIST database match and can use retention indices to assist with identification as well. Of course, it is always ideal if you do think you're working with a novel, a new biomarker. Running an analytical standard is always recommended for final identification, but we can get good matches to our database here. Going beyond breath, I think I've been able to show that TD is a nice, convenient way to present breath samples to a GC/GC-MS approach. We also have the ability to look at VOCs in other biological samples as well. And for this, a lot of times it's best to shift away from a TD tube and move to something like classical SPME fibers or direct headspace, or something. And you can think of this as just a John. And for this, we have another TD unit known as a Sentry. And you can think of this as just as a TD with a fairly standard CTC rail plopped on top that allows us to introduce these samples through our focusing trap and to GC/GC-MS for detection and analysis. So looking at one study performed by a collaborator, we have a sorptive extraction, or again, high sorb, performed in direct immersion of human urine. This was looking for significant differences between a control group and those with pancreatic ductal endocarcinoma, or PDAC. And what they had found were paracymene and paratresol upregulated in the affected group for the study. Another example of a different type of sampling approach is the use of thin film SPME for the analysis of skin VOCs. For this, we can essentially take a thin film membrane, place it directly on the human skin. Though I shouldn't say directly, it's always good to put a little layer of something like a steel mesh there, or you're going to see just a whole bunch of hexadecanoic acids and other fatty acids overload your chromatogram. And all this thin film really is if I mentioned that a high sorb was a giant SPME fiber, a thin film is a giant SPME fiber that has been prepared in a flat morphology, making it really useful for sampling of surfaces. But this gives about 26 times greater signal in the pre-equilibrium phase because of its 26 times greater surface area. And if we do allow it to extract for equilibrium, we can see 2 orders of magnitude of signal improvement just from the sample volume. These are then just inserted into an empty thermal desorption tube and desorbed on the system. So I think Heather had alluded to this as well. One of the potential downsides that can come about with when you're using high volume samplers and even standard SPMEs, we see a lot of backgrounds from those devices, particularly the siloxanes. This is where marrying thin film SPME with GC/GC is so nice, because those siloxanes are going to fall out down along with a lot of your alkanes, but down along the bottom of the plot, where other compounds of interest, like our fatty acids, will then be separated out on the second dimension chromatogram. And we can look at these independently away from the background interferences. Second last study I'll quickly mention is the analysis of fresh versus aged blood. This was done by collaborators at University of Liège, essentially collecting blood samples from 3 different individuals and then aging them for 1 to 7 days. Essentially, they would replace the lid on top of this jar, put an active pump sample to pull this into a TD tube, and then use multivariate statistical processing, the aforementioned Fisher ratio tile-based approach, to look at the differences in that age blood. So just as a very quick show of that methodology. The last one I'll talk about today, this one I found very interesting myself, is the analysis of even something like breast implants, which I think it lines up quite nicely coming after the high Zorb and thin film approaches, because those are typically divinylbenzene polydimethylsiloxane as your sorbent on those. Well, what is a breast implant besides a giant polydimethylsiloxane or PDMS silicone sampler implanted in the body, passively sampling for the 10 years this was in the patient? I believe for sample prep on this one here, this was just back extracted with a organic solvent and liquid injection onto the GC. However, I would actually be really interested in sticking just a little square one of those implants in a TD tube and seeing if we can desorb it just like a PDMS membrane. But as an analog, that PDMS is very nonpolar, and it's going to pick up bioaccumulants just like our fat tissue would over the duration in the body. And interesting enough, in that very, what I'd say messy, but very feature-rich, shall we say, chromatogram, you can see DDE being extracted and being present in that body, which makes sense, as we know this is quite a common bioaccumulant. So with that in mind, I'll quickly, I think I'm pretty close on time, so I won't spend too long in the summary here, but I think I've been able to show that I do believe TD is showing itself as a new gold standard for breath approaches, for direct collection of breath onto that tube, followed by analysis. We've been able to then demonstrate the usefulness and the importance of good separation through GCGC to help us identify and see unknown samples, particularly at trace levels in those samples, and then the usefulness of good mass spectrometry and data processing to make sense of all that data we're seeing. So with that in mind, I thank you all for your attention and take any questions you may have. Thank you.
Thank you so much, Jonathan. Floor is open to any questions.
I'll kickstart. So I've had a lot of previous conversations with David regarding the tiling approach. And because right now we're trying, just to be open, we're trying to find a nice spectral alignment algorithm to align a healthy data set. And we're really strong. I think that's a really big problem in the field, is that a lot of the spectral alignment algorithms just give erroneous features that are not real or high fidelity. So the tiling approach is only good for compounds that display some significant difference by the Fisher ratio. What about things that don't change? And then moreover, how do you account for false discovery if you don't know the entire pool of features?
So I'll answer the first part there. Well, firstly, as you had alluded to, alignment becomes very important in making sure that the features that are then eventually identified by the Fisher ratio analysis is reliable. So one thing I forgot to mention in my talk is we typically will run an automated alignment. Automated alignment using a reference sample. We'll typically try to select not the first run made, because there's more likely to be retention time drift in that sample. And then make sure that features that occur in a given grid, in a given tile, are occurring at that same time from run to run to run, accounting for retention time drift. As you had mentioned, if samples are shown, given features are shown to have similar amounts of signal from run to run, we're not going to see that difference. So what we typically try to do in conjunction with our tile-based approach is we will also still generate, much like Dr. Alonso had shown with his, our peak tables, looking at relative signal in our runs. One thing we like to do to help with that, to see if we have other features that are of interest that we've missed with the Fisher-based analysis is we will simultaneously split between our TOF and an FID, which is of course known to have much more repeatability in terms of signal. And then when we generate our peak table, we'll look at that signal from the FID runs, compare it to the TOF data to see if we have other features using a more classical approach, and look for increases and decreases across the groups. Sorry if that was a bit of a roundabout answer there.
No, thank you so much. Yeah. So what you said you did an alignment like after the tile? Like how did you do that? What software did you use?
Back here. So it wasn't actually after the tile. So before we run our chiral-based approach, in Chrome Compare Plus, we have a feature known as automated alignment. And essentially what that will do is we select one reference chromatogram. And again, we typically try to pick a chromatogram that is not the first one run, as that one is most likely to have retention time shifting. The software will then automatically look into that data file, and it will identify, let's say, reference peaks throughout that chromatogram, looking at the MZ ratio across a given peak. And then it will redraw every chromatogram done in that cohort. So you'll get a new data file where the retention times have actually been shifted to align to the reference chromatogram. That way we ensure that given peak occurs in the same grid from run to run to run, when we then submit that to the Fisher-based tile approach for picking out significant features. Because just as you said, if say in one run, this peak is in this grid here, and then suddenly in the next one it's over here, that could result in false negatives of not picking up a peak in one sample.
I was more talking about intensity of signal, not retention time drifts. It's only picking up compounds that have a differential intensity across two classes, and not things that stay the same. I
mean, it will still show things that are the same and potentially significant of significant interest. Let me go back here. But it may miss, depending on how your confidence is set, you may miss some of those features. So we do try to highlight compounds that are the same between the two groups and that have significance to the similarity, so enough signal, and the error is consistent enough to demonstrate that. But I'm not sure if that answers your question there.
Yeah, but like here, I think this actually illustrates the kind of what the base of the volcano plot is missing.
Yes.
Yeah. So yeah, that's kind of my concern.
And that is where we do typically recommend, all depending on how deep you want to go into the data. In addition to doing this multivariate approach, it can still be quite beneficial to generate your peak tables, compare that to a detector that has very low RSVs, so the relative error is less, splitting to an FID, and then look at the variation across your peak tables. But that is a little bit more intense for the end user to do, for the researcher to do.
But maybe worth it though.
Yeah.
Thank you so much.
Thank you.
Thank you for the discussion. For the sake of time, we're going to move on to Dr. Heather Bean's talk. Jonathan, I did get a question in the Q&A that I'm going to DM to you, and then if you would be kind enough as to reply maybe in the all chat for everyone to see, that would be awesome. If not, you'll still get the question from me regardless. So last but most certainly not least, we have Dr. Heather Bean. She is an associate professor in the School of Life Sciences at Arizona State University, where she is a bioanalytical chemist that specializes in untargeted volatilomics using 2D GC time-of-flight mass spec. Her research team characterizes the volatilomes of humans, animals, plants, and environmental microbial consortia with two main purposes. One, developing novel biomarkers and diagnostics with an emphasis on breath tests, and two, investigating the roles of volatile and semi-volatile metabolites in mediating microbe-microbe and host microbe interactions. We can see your slides, so whenever you're ready, please take it away.
Thank you so much for the introduction, and thanks for the invitation to present today. I have benefited a lot from having some great science and introductions from my colleagues today. So I'll be telling you about an application of many of the things that you've already heard about. Okay, so I need to give a disclosure and a disclaimer for this work. I'm on the Scientific Advisory Board for Shirley Diagnostics Public Benefit Corporation with an equity stake in that company. And the work that I'll be telling you about today is supported by the Defense Advanced Research Project Agency, or DARPA. And the views, opinions, and findings contained in this material are those of me and my co-authors and should not be interpreted as representing the official views or policies of the Department of Defense of the U.S. or the U.S. government. No official endorsement should be inferred. Just to give you a quick taste of what we do in my lab, Arai already introduced it briefly in his introduction. Our group specializes in comprehensive two-dimensional gas chromatography, and we apply this tool to discover novel volatile metabolites and the ways that they are used in biological systems. And we also leverage the information that we discover for developing non-invasive diagnostic tools, such as through breath testing. We, as Arai mentioned, we do study microbial interactions that are mediated by volatile organic compounds. My longstanding work has been in disease biomarker discovery. So for instance, differentiating pneumonia that's caused by a fungus called valley fever from other types of pneumonia is an ongoing work in my lab. And more recently, we've gotten into some work on performance monitoring, and that's what I'll be talking about today. So this study, fatigue assessment via breath, or the FAB study, our goal was to develop a breath test that can identify the types of fatigue and quantify fatigue levels. And what I'm going to be focusing on today is our work on identifying biomarkers that can tell us about the type of fatigue, as well as the differentiate minimum versus maximum fatigue states. And the types of fatigue I'll be talking about are physical fatigue, mental fatigue, and sleep deprivation. The study team was large. The study was, the PI was Ruzba Jafari. He was at Texas A&M University. He's now at MIT and recently joined DARPA. Ranjana Mehta is at the University of Wisconsin-Madison, and she's the fatigue expert on this study. Stephen Riekman is at Texas A&M. He's a kinesiologist, and Ivan Ivanov at Texas A&M University is the biostatistician. And then we had many trainees on this study. Dr. Trenton Davis, Aaron Simmons, Lead Sue, and Sean Stenell are really our sort of team leads for this study. And then we had many more graduate and undergraduate students who worked on this. So for this study, this was all entirely a lab-based design. We recruited 66 young, healthy, fit individuals that are represented by 41 males and 25 female participants from the area in and around Texas A&M University. For the study, these participants came in 5 weeks in a row for 5 different fatigue sessions. In each fatigue session, they were either exposed to a single etiology of fatigue, so they either underwent a protocol to induce physical fatigue, mental fatigue, or sleep deprivation. And they also, in other weeks, experienced combined etiologies of fatigue. So, for instance, they went through a protocol that simultaneously induced physical and mental fatigue, or they experienced sleep deprivation and mental fatigue, for instance. For this study, we controlled their nutrition for the day before they came into the experiment and during the time that they were in the lab, which means that they were provided with boxed meals. Everybody received the exact same meal. So we were trying to control variations in diet to an extent. And foods that are known to have volatile profiles in breath, like garlic and onions, were removed from their diets 24 hours in advance. The way the fatigue was induced was for physical fatigue. They underwent 30-minute blocks, 4 of them in a rapid time sequence where they were wearing 47% of their body weight in a rucksack, and then they were on a treadmill going at a high pace to maintain a high level of exertion. For the mental fatigue, they underwent 4 30-minute blocks of a mental taxing exercise called a 2-back test. And for these 2 protocols, we took their breath and a whole battery of fatigue measurements before they started the protocol. And then at every, there were 5-minute breaks in between the fatigue blocks, and we collected breath and a battery of fatigue measurements at each of these interblock time points immediately after they finished the 2-hour session, and then 30 minutes later and 60 minutes later after recovery periods. For sleep deprivation, the participants underwent 28 hours of wakefulness. They woke up at 7 a.m. on the day that they reported to the lab, and then they stayed with us until 10 a.m. the next day. And we measured their breath samples and collected fatigue measures in 4-hour blocks. So the first measure was at 6 p.m. And then they were measured again at 10 p.m., 2 a.m. the next morning, 6 a.m. the next morning. And then the final measurement was at 10 a.m. the next morning. But the participants also then stayed on and engaged in either that physical fatigue protocol or the mental fatigue protocol so that we could get those binary modes of fatigue, sleep deprivation plus physical fatigue or sleep deprivation plus mental fatigue. And when they went into those sessions, we then collected the same samples that I mentioned before. So for this study, we wanted to develop breath biomarkers that could differentiate their state of fatigue at the time that they came into the lab, so before they engaged in that fatiguing protocol versus the endpoint in time. Our overall steps for doing this, we collected breath samples and we stored them on thermal desorption tubes. And we did use Tedlar bags, as was described in prior study. These are 3-liter Tedlar bags, and we collected expiratory reserve volume breath, which is the breath that comes after the end tidal breath, so that we were ensuring that we were collecting a lot of good representative blood VOCs. Once the breath samples were transported to us at Arizona State University, we performed untargeted analysis using a LECO Pegasus 4D instrument, and the data processing was performed by Chromatoph Tile. In the end, after we cleaned up the data and removed any samples that were out of compliance, our final data matrix was 2,513 breath samples, and there were over 3,100 breath features in the data matrix. Then we're doing many different studies with this data set. Our next steps for any of our studies is going to be machine learning and to identify putative biomarkers and develop classification models, and then to assess those diagnostic performances of those models. And then the markers that are performing well, we did chemical identification on those compounds. And what I will focus on for the rest of my presentation are these next 2 steps of the machine learning approach, our chemometrics approach, and then show you the results of what we got from this study. For our first study, the one I'm going to tell you about today, we wanted to identify breath features that can discriminate or between minimum fatigue and maximum fatigue. And in this case, we're going to use our time on task. So we developed a separate biomarker breath model for physical fatigue, a different one for mental fatigue, and then another one for sleep deprivation. In creating the classification model for physical fatigue, we looked at the breath samples that were collected before they started their fatigue protocol and the breath samples that were collected after they completed that 120-minute protocol, and used these as the minimum fatigue state versus the maximum fatigue state for physical fatigue. The same design was used for mental fatigue, 0 minutes versus 120 minutes of time on task. And for sleep deprivation, we used as the minimum fatigue state when they had been up for 12 hours. So that's when they reported to the lab at 6 p.m. And then we took the second maximum fatigue sample that we used was after they were awake for 28 hours, which was collected at 10 a.m. the following day. So for our chemometrics approach, for our machine learning, we went through 5 major steps for this. And the first step is that we did feature selection, and we used 2 different mathematically unrelated machine learning approaches in order to identify out of the 3,100 features that were in our data metrics, the 20 to 50 most important features for discriminating that minimum versus maximum fatigue state. We used random forest and we used ElasticNet. So for this feature selection step, we went through 100 iterations where the data were split into an 80% training, 20% validation set. And we then combined the information from the 100 iterations of random forest and the 100 iterations of ElasticNet to identify the common important features for the random forest and ElasticNet models. And then we assessed the performance of these initial feature selection models using area under the receiver operator curve and sensitivity specificity, but I will really focus on AUROC today. To build our final classification models, we took the important features from random forest and ElasticNet for each fatigue etiology and combined them into a union set. This was our down-selected set of important features for each fatigue etiology. We then put them back through new random forest and new ElasticNet models using an 80-20 training validation split again. At this stage, we again assessed the model metrics and evaluated the important features for each of the models. And then after we built these models, we froze them and we tested those models on held out data. I won't be showing you this data today. We're so close to having it finalized, but I will be showing you the data from the feature selection process and the model training and validation process. So what we saw is an interesting and somewhat surprising. I didn't expect such a boost, but what we saw from our models that were built where we used all 3,100 breath features, if we're predicting and trying to classify minimum fatigue versus maximum mental fatigue, we observed that those initial feature selection models, the random forest performed at an AUROC of 0.64. Below is our confidence interval range for that measurement. And for the ElasticNet models, we saw model performance of 0.73. But then when we built new models on our selected features, we got a massive boost in performance for the models. And we've been doing this now for other studies that we've been conducting where we have multiple orders of magnitude more features than samples, and we're seeing the same story over and over again. So for the final models, For random forest, we saw a boost up to a 0.89 AU ROC, and for ElasticNet, a 0.99 ROC. And the same story happens when we look at our binary classification models for physical fatigue and for sleep deprivation. We're always seeing a good but modest performance when we use all 3,100 features. And then we see a significant boost in performance once we've restricted the feature space to build the final classification models. We wanted to take a look at how well conserved the important features were between the random forest models and the ElasticNet models, and we saw different things depending on the fatigue etiology. So for the mental fatigue models, first of all, there were very few really conserved important features for a random forest model. There were only 7, and there were 41 that we included and deemed important features from ElasticNet, and they shared only 5 of those important features. But it was a different story for the physical fatigue and the sleep deprivation, where the random forest feature set was larger, but then it also had much more overlap and shared features with the ElasticNet models. We were curious about how much overlap there was between different fatigue etiologies in these important features. And so we looked only at the data I'm going to show you is when we looked only at the features that were conserved between the ElasticNet and the random forest models. We wanted to see if there were overlaps in these 5 features with these 18 and these 13. And what we observed was really interesting to me. We see that the physical fatigue is something entirely its own. There are no shared features to discriminate between baseline and maximum physical fatigue compared to the models where we're looking at baseline versus maximum mental fatigue and baseline versus maximum sleep deprivation. However, there's significant overlap between mental fatigue and sleep deprivation as far as the important markers that indicate those maximum fatigue states. And I think just as a layperson, we sort of understand and recognize that when we are sleep deprived, we also feel more mentally fatigued in those states. And there are some shared underlying physiological pathways to back this up. Next, we wanted to explore what happens if we build classification models that differentiate a maximum physical fatigue state versus a maximum mental fatigue state versus a maximum sleep deprivation state. We wanted to find out, could the biomarkers discriminate between the type of fatigue or the etiology of fatigue? We even though we independently started from scratch from the 3,100 markers and did feature selection, and we saw the same result as I'm about to tell you about, another approach that we took was our feature selection step was all the work that we did in the minimum versus maximum fatigue modeling. So we took the collection of important features from random forest and ElasticNet, physical fatigue, mental fatigue, and sleep deprivation, and use those as our selected features to then build what we call this multi-max fatigue discrimination model. And what we saw from this is that the model could differentiate and identify the physical fatigue state at a sensitivity of 0.95 and a specificity of 0.91. It could identify the mental fatigue samples with a sensitivity of 0.73 and specificity of 0.91. And the sleep deprivation fatigue at a sensitivity of 0.73 and a specificity of 0.88. And we, the samples that are being confused for each other are when there is misclassification are the mental fatigue samples. Some of them are being misclassified as sleep deprivation, and the sleep deprivation samples, some of them are being misclassified as the mental fatigue. And it's not surprising. They share a lot of breath features and chemical information. And again, if we start from scratch from the 3,100 features, we get the same results, same sensitivities and specificities, same overlaps between the mental fatigue and sleep deprivation markers. So to summarize, through this study, we have been able to demonstrate that breath biomarkers can discriminate between minimum and maximum fatigue states when we are defining maximum fatigue as maximum time on task, and the models are very accurate. We're also able to use that same suite of biomarkers to discriminate between physical fatigue versus mental fatigue versus sleep deprivation as the cause of the fatigue. And we're seeing that feature selection is actually an important step, even for modeling approaches like random forests, which are quite robust against overfitting. We see a significant model performance boost when we first do feature selection and go down a couple orders of magnitude in the number of features that we're feeding into those models. Again, I want to acknowledge the team. Here's a larger list of the graduate students who participated in this study. And on my team, Dr. Chintan Davis was really the thought leader in my group on this work. We also had really significant support from Darshan Zabin and Bilal Ali. And I'll take any questions.
Thank you very much, Dr. Bean. There are a couple questions. There are 3 questions in the chat from Mark. So the first one being, how much were the participants paid in the study?
That's a good question. I don't remember the exact number, but we had to pay them, and we found out actually that we needed to stair step the payment and really encourage them to stay in. So early on, we not all 66 participants did all sessions. We got 60 to complete all sessions. I think they were paid around $1,000 to complete all sessions. There was also 2 weeks in which they had to do pre-screening and testing. We also monitored their sleep and activity and heart rate round the clock for 7 weeks. But in the end, we did settle on an approach that we got really good retention. And large part of it was giving them a substantial bonus for completing all 5 sessions.
I love that. That's awesome.
We have to take note of that for future
Yeah, we do.
studies.
Exactly.
Yeah, I'm happy to chat with you offline to tell you we can give you our exact payment scheme. We did have to iterate and figure out what worked.
Makes sense. Thank you. Next question also from Mark. What do you see as benefits to using Tedlar bags? Many view this as an outdated technology, but I'm in full support of bags.
Yeah. So one of the reasons that we use Tedlar bags is the cost. Even though they're disposable, this was a single site study, but many of the studies that we run are multi-site. And if we wanted to purchase a unit that is for breath collection, they are expensive. And having the upfront money in order to purchase those units at multiple sites can be cost prohibitive oftentimes. So for many of our studies, we use Tedlar bags. The second is that we also do studies in some cases in highly infectious organisms, and infection control practices are of immense concern, and I mean in the clinical setting. And so we've found it easier to get approvals to use disposable breath collection materials versus demonstrating that a reusable device has been properly sterilized between sending it to different patient rooms. I don't love how much waste we use, but those are our 2 main drivers for using Tedlar bags. It's very practical reasons as far as getting studies done.
Can you, beyond like the contaminate, an infectious disease, throw the bag out, but like say a healthy volunteer, have you run studies where you like, can you reuse a bag? Or is there like cross-contamination after you breast sample?
We we haven't tried reusing bags. I think there've been some studies on this, and you need to do flushing at a minimum to get the water out of the bag, and then to, anything that's adhered to the walls. But that's not a practice that we have been using.
Yeah, what our motto is if we don't test it, we
Yeah.
don't do it. So
Right.
even potentially wasteful, but anyway.
One more question. Is there a difference in VOC signal or reproducibility between the alveolar phase and post-expiratory reserve that you were describing?
No, I doubt that there is, but we didn't do this study. The reason that we use the expiratory reserve volume is that, and let me describe in a little bit more detail what that is. So the end tidal breath is the very last part that you exhale in just relaxed, easy breathing, normal breathing. And it's more or less defined by an increase and then a steady state of CO2 in your breath, reflecting that you are capturing alveolar air where gas exchange has occurred between the blood and the breath. We tried to get approved to add a capnograph for our study, but our sponsor slashed that out of our budget. So our approach was to, okay, let's collect the breath that's after the last part of the breath, out of that, after the end tidal breath. And the expiratory reserve volume is after you do just a full easy exhalation, you can actually push more air out of your lungs. That's the fraction we captured because we knew it would be blood gas. And it was just really easy to train people to do that protocol. And we did do training on a capnograph so that they could see what was happening with their CO2 and understood why we were capturing that expiratory reserve volume. So we've never done the comparison, but it was just our approach to be able to do this study without utilizing a capnograph.
Yeah, that's a huge because we're trying to do like a fractionation on the fly thing, and we might get questions about it, and maybe your approach is just an all-around better way to really ensure. I mean, yeah, you'll have to do more breaths, right? Because you're getting
Yes.
a smaller volume, but there's
Yes.
no doubts that your CO2 is plateaued.
Yeah, part of what we wanted to do was a field study as well, again at multiple sites, and that's where the sponsor was like, No, you need a different system to where you're not going to need to rely on a capnograph," and that's why we turned to expiratory reserve volume.
Awesome. I don't think we have any Q&As in the queue, yeah, in the actual designated box. So we'll just wrap up here. Thank you everyone for attending. We had a really good turnout, including those who stayed on for the entire webinar. So thank you so much. We also have Dr. Mangalal Agarwal on the line, who's my PI, my big boss, and he's been in full support of this webinar, and he could take the floor away for a couple words. Thank you for coming.
No, thank you, Mark. I really, first of all, these were really wonderful talks and a great webinar. I want to thank you for uh, making this happen, and also the MDPI separations group for hosting this, and all the wonderful speakers we had today. And from me personally and from the Institute, we want to thank all the participants and the speakers. Thank you.
All right, Arai, take us home.
I think everything has kind of been said. Today we saw a wonderful mix of biomarker discovery work as well as approaches to advanced analytical instrumentation and kind of the instrument-based innovation that is going on within our field, which I think is both very much needed, but also just highlights the need for more cross-disciplinary studies and shared approaches towards things like sampling, especially without a universally accepted breath sampling method, for instance. That's kind of been the headache of my entire PhD, actually. So hopefully with time, it gets better, and the only way we can do that is by continuing to have webinars like this and share information and, keep collaborating. So thank you everyone who, obviously to our speakers first, and then to everyone.
You cut out, Araya, I think.
Oh, yeah, sorry. I was just saying thank you to all the speakers again, and then everyone that participated in a very fruitful discussion. And that wraps up our webinar. So, and then, yeah, take a look in the chat. There are reminders on the special issues that have been mentioned. There are also the recordings that will be available, as well as for the people that need a certificate of attendance to this webinar. There's a link that I've provided in the chat. Please go to that within 30 minutes of this webinar ending to receive your certificate. It should be all the way up somewhere with SciForum. Or yeah, the second last message by Jamie. So yeah, thank you everyone.
Thank you. Let's keep in touch. Take care.